Okay, so today we're going to be diving into something pretty cool in the world of video AI.
Sounds good.
It's a paper all about STORM.
STORM.
Yeah, Spatiotemporal Token Reduction for Multimodal LLMs.
Catchy.
It is catchy, right?
Yeah.
But more importantly, it tackles this really fundamental problem in video understanding.
Okay.
How do we efficiently make sense of these super long videos without drowning the LLMs in data?
Yeah, that's always the issue, right? Too much data.
It is.
Yeah.
Right now, we kind of treat videos as just stacks of independent images. It doesn't really work that well when you have hours of footage.
No, I mean, you lose all the context of what's actually happening over time.
Exactly, and that's exactly what this STORM paper addresses. They've come up with this really interesting architecture where they introduce a dedicated temporal encoder.
A temporal encoder.
Yeah, and they use this model called Mamba, which has been getting a lot of attention for efficiently handling these really long sequences.
Yeah.
And they stick this temporal encoder right between the image processing part and the LLM.
Okay, so it's like an intermediary step to kind of pre-process the temporal information.
Exactly. And what's really wild is that it not only makes the whole thing way more computationally efficient, up to 8 times less computation.
Wow.
But it also significantly improves performance on these long video understanding benchmarks by over 5%.
That's impressive. So how are they getting these gains? What's the secret sauce?
Okay, that's what we're going to unpack right now. We'll take a closer look at how this temporal encoder works and how they're being smart about reducing the number of tokens that the LLM has to deal with.
Okay, so for all of our listeners out there who are really pushing the limits of video analysis with large language models, this is going to be a good one. This ability to handle longer videos more efficiently and accurately could really change the game for a lot of applications.
Absolutely. And then I think a good starting point would be to kind of dissect why these existing approaches for video understanding with LLMs have been struggling, especially with longer content.
Yeah, I think the paper really nails this when they talk about the standard approach.
Which is?
Well, it's actually quite straightforward. You take your video, break it down into individual frames.
Okay.
Then you run each frame through an image encoder like CLIP, or in this case, they use SIGLIP.
Right.
And then you basically project those visual features into the same space as your language model. Architectures like Video-LLMs, for example, they're built on this very foundation.
So each frame is treated as its own separate entity.
Yeah. And for short videos or tasks where you're mostly focused on what's visually happening within each individual frame, this approach can work all right, but the cracks start to show when you try to go beyond those short snippets and deal with videos that have a longer time span.
It's kind of like trying to figure out the plot of a movie by just looking at a bunch of random stills.
Yeah. Exactly. You miss all the nuances, the character interactions, the flow of the story.
And I imagine when you scale that up to hundreds or even thousands of frames, the LLM just gets overwhelmed.
Oh, absolutely. And remember those attention mechanisms that LLMs rely on? They have this annoying computational complexity that increases quadratically with the sequence length.
So the longer the video, the more computationally expensive it becomes.
Exactly. It just explodes, and it quickly becomes the main bottleneck preventing us from analyzing those longer videos effectively.
So what have people been doing to kind of work around this problem?
Well, the most common workaround is frame subsampling.
So basically just pick in a few frames here and there and chuck in the rest.
Pretty much, it's a way to make the computation manageable, but as the paper rightly points out, it's a very crude solution.
Because you're essentially gambling on which frames are important.
Yeah, you could end up throwing away crucial information like that one frame that explains the entire scene, or the subtle facial expression that changes the whole meaning of the interaction.
And I guess the other issue is that even with subsampling, you're still processing a lot of redundant information.
Right, consecutive frames often have a ton of overlap visually.
So you're spending all this computational power on essentially the same data over and over.
Which isn't very efficient at all.
This is where STORM steps in and proposes a pretty radical departure from that traditional way of doing things.
It's a really elegant solution. They introduced this dedicated temporal projector right into the architecture. And they base this projector on the Mamba State Space Model, which, as you mentioned, has been making waves for its ability to efficiently deal with long sequences.
Okay, so instead of treating every frame as an isolated unit, they're incorporating the temporal dimension right from the get-go.
Exactly. And they do this by strategically placing this temporal encoder between the image encoder, like the SIGLIP they used, and the large language model.
I see. So it's like a bridge between the visual information and the LLM.
Yeah, a bridge that's specifically designed to enhance the visual data with an understanding of how things are changing over time.
Before it even hits the LLM.
Precisely. And by integrating these temporal dynamics early on, they're hoping to achieve two main things.
Okay, what are they?
First, they want to significantly boost the model's ability to reason about time, to understand the flow of events.
Makes sense, because if you're feeding the LLM tokens that already contain temporal information, it doesn't have to try and figure it out on its own.
Exactly. And second, by reducing the computational burden on the LLM downstream, they're aiming for a much more efficient system overall.
So it's not just about performance, it's about making the whole process more manageable.
Absolutely. And this is where Mamba comes in.
This Mamba State Space Model.
Yeah, it's really quite fascinating.
That makes it so special.
Well, unlike those traditional recurrent neural networks or even the transformer architecture that you see in most LLMs, Mamba uses this selective state space mechanism.
Okay, I'm not super familiar with state space models. Could you maybe break that down a bit?
Sure. So think of it as this incredibly efficient filter that can look at the entire sequence and dynamically choose which parts of that sequence are crucial to remember and which parts it can safely discard.
So it's not giving equal weight to every single input.
No, it's being very selective. And this selectivity is key to its efficiency, especially when you're dealing with long sequences.
And how does it compare to the attention mechanisms that we see in transformers?
That's the really cool part. The computational complexity of Mamba scales linearly with the sequence length.
Linearly meaning?
If you double the length of the video, the computation time roughly doubles.
Okay.
But with transformers, the complexity is quadratic.
Meaning it increases much faster.
Much, much faster. So if you double the video length, the computation time could quadruple.
So for those really long videos, Mamba has a huge advantage.
It's a game changer.
And the paper highlights this interesting dual functionality of the Mamba layer.
Yeah, so imagine you just feed it a single still image. In that case, it acts like a spatial scanner. It enriches the tokens that represent that image with a broader understanding of the spatial context within that single frame.
So it's like it's looking at the relationships between different objects and regions within the image.
Exactly.
But then when you feed it a sequence of video frames, it shifts gears and becomes this spatiotemporal scanner.
It starts capturing information not only within each frame, but also across the entire sequence over time.
So it's like it's building up this internal representation of how things are moving and changing.
Precisely. It's creating tokens that are no longer just snapshots in time, but summaries of the video's evolution.
And this is where that whole token reduction idea comes in, right?
Exactly, because now each token carries so much more temporal information, they can be much more strategic about how many they actually feed into the LLM.
You don't need to bombard the LLM with every single detail.
Right, they can reduce the overall number of tokens without sacrificing the crucial context. And to really capitalize on these enriched tokens, Storm introduces a couple of different token reduction strategies.
Let's hear them.
So they've explored both techniques that can be applied during inference without any extra training, and then methods that are actually incorporated into the training process itself.
Got it. So like real-time adjustments versus something that's baked into the model.
Precisely. Let's start with the real-time stuff, the test time temporal token subsampling.
Okay, so this happens after those visual tokens have already gone through that Mamba-based temporal projector.
Yes, so they've got all that added spatiotemporal richness, and now you can be a bit more picky about which tokens you actually send to the LLM.
I'm guessing it's not as simple as just randomly dropping tokens.
No, it's not random at all. The key is that because these tokens are already packed with temporal information, you can subsample them in a way that preserves the important temporal cues.
So you're not losing those crucial transitions or moments of action.
Exactly, and what's interesting is that the paper mentions that this subsampling not only cuts down on the LLM's workload, but sometimes it can even lead to slightly better performance.
Really?
Yeah, because it can help filter out some of the noise that comes from those redundant frames.
That's a win-win.
Now, on the training side, they delve into these training-based token compression techniques with two main approaches, temporal pooling and spatial pooling.
Okay, so temporal pooling first.
The basic idea here is that you often have consecutive frames that are very visually similar.
Right, like 2 frames in a row where the only difference is a slight movement.
Exactly. So instead of processing each of those frames separately, they apply this pooling operation across those similar frames.
So they're grouping similar frames together.
Yeah, and they use temporal average pooling specifically. So they take a small window of consecutive tokens and they average their values together over time.
Okay.
And this creates a single new token that represents the information across that entire little chunk of time.
So you've essentially compressed multiple frames worth of information into one token.
Precisely. And because the Mamba module has already done the heavy lifting of capturing the temporal relationships, this averaging process doesn't lose the crucial context.
It's just getting rid of the redundancy.
Exactly.
Now, what about spatial pooling?
So spatial pooling is applied to each frame individually after it's been through the Mamba module.
Okay, so it's working on the spatial dimension within a single frame.
Right. They take all the tokens that represent that frame and they apply average pooling across the spatial dimensions.
So for each moment in time, they're further reducing the number of tokens.
Exactly. It's like an extra layer of compression to make everything even more efficient.
And both of these pooling techniques are all learned during the training process, right?
Yes. So the model figures out the best way to compress the information without throwing away the important stuff.
That's pretty cool.
And it's worth mentioning that these different token reduction methods, the temporal pooling, the spatial pooling, and that test time sampling, they can be used in different combinations.
So you can mix and match depending on what you need.
Exactly. It gives you a lot of flexibility.
Okay, so we've covered the architecture, the temporal encoder, the token reduction strategies. It all sounds very promising. But what I really want to know is, how does this actually translate into real-world results?
That's the million-dollar question, right?
Does it actually lead to better performance and efficiency?
Well, the paper does a really thorough job of evaluating Storm across a bunch of different long video understanding benchmarks, and the results are pretty impressive.
Lay it on me.
So they consistently achieve state-of-the-art performance, especially when they combine temporal pooling with that test time temporal sampling.
I remember you mentioned they outperformed other open source video LLMs.
Oh yeah, by a significant margin on benchmarks like MVBench, MLVU, Long Video Bench, and Video-M.
And they were even competitive with those big proprietary models like GPT-4v and GPT-4o.
In some cases, even outperforming them.
Wow, that's huge. Especially considering they're doing all of this while using significantly fewer tokens.
Yeah, they managed to compress those visual tokens down to 25% with just temporal pooling, and a tiny 12.5% when they combine it with test time sampling.
So they're addressing that computational bottleneck head on.
Exactly.
Now, what about that Mamba module itself? Did they test how much of an impact it was making?
They did. They compared Storm to a baseline Vila model, which didn't have the Mamba-based temporal encoder. Even without any pooling or subsampling, just by incorporating Mamba, they saw noticeable performance gains.
So that temporal encoder is really doing its job.
It is, and it gets even better when they added the test time temporal sampling to Storm. They got a 43% reduction in inference time, and the performance either stayed the same or actually got even better.
You're getting faster processing without sacrificing accuracy.
Exactly. Which really highlights how effectively Mamba is capturing and propagating that temporal information.
The tokens are so rich with temporal context that you can afford to discard some of them without losing the overall understanding.
Now let's talk about that temporal pooling during training.
Okay.
By using temporal pooling, they could train their models on much longer video sequences, up to 128 frames, while using the same computational resources as training on just 32 frames without temporal pooling.
So you're essentially getting more bang for your buck during training.
Precisely, and the results were quite impressive. They saw performance improvements across all the benchmarks and a massive 58.4% reduction in inference latency.
So not only are the models learning more effectively, but they're also running much faster.
And then when they combined temporal pooling with test time sampling, they got even more efficiency, a 65.5% reduction in inference time, and they were using only 12.5% of the original tokens.
That's incredible.
It is, and all while maintaining very competitive performance.
Now, I remember you mentioned they also did a comparison between temporal pooling and spatial pooling for those longer videos.
Yeah, and it really highlights the importance of explicitly modeling the temporal dimension.
How so?
Well, spatial pooling could hold its own for shorter videos, but for those really long ones, 128 frames temporal pooling consistently gave them better results.
And why is that?
Because it seems like temporal pooling is much better at capturing those long-range dependencies in the video, those relationships that span across many frames. And to further show how important Mamba is, they looked at how the performance changed as they trained the models on longer and longer videos.
Okay.
Storm actually got better and better as they increased the video length during training, but the baseline model without Mamba started to plateau or even get worse.
So it's like Mamba is the key to being able to effectively compress the video without losing the essence of what's happening.
Precisely. And to add to all of this, they also found that incorporating Mamba didn't add a huge overhead to the training process.
That's good.
Only about a 5% increase in training time.
Totally worth it for those performance and efficiency gains.
And they didn't stop there. They also wanted to make sure that their model wasn't just good at getting high scores on benchmarks.
Right. It needs to actually understand the content.
Exactly.
So what do they do?
Well, they did some qualitative analysis to see if the model could still extract relevant information even after they compressed the heck out of the video. It did. Even when they reduced the number of tokens by a factor of 4, the model could still do things like correctly identify the author of a poem mentioned in the video or accurately count the number of news segments.
So it wasn't just blindly guessing, it was actually paying attention to the details.
And they even did a category-level analysis on Video-M, showing that Storm consistently outperformed the baselines across most task categories, including those that rely heavily on optical character recognition.
That's impressive.
And to really put their architecture to the test, they didn't just stick to one specific configuration.
They mixed things up.
They did. They tried different LLMs, different vision encoders, even different model sizes. The core Storm design consistently showed improvements in both performance and latency across all these different setups.
So it's a pretty robust and versatile approach.
Absolutely. And finally, they really emphasized those efficiency gains by showing how that latency gap between Storm with compression and Storm without compression just gets wider and wider as the video length increases.
So the more complex the video, the more important that token reduction becomes.
Exactly.
So to wrap it all up, it seems like Storm is making some really exciting progress towards solving this fundamental challenge of understanding long videos with LLMs.
Definitely by incorporating that Mamba-based temporal encoder early on and then using these intelligent token reduction strategies, they've managed to create a system that's both high-performing and remarkably efficient.
And what does this mean for all the researchers and engineers out there working on video analysis applications?
Well, it opens up a whole new realm of possibilities for analyzing those really long videos efficiently and accurately.
Things like analyzing hours of security camera footage or understanding complex medical procedures.
Exactly. Tasks that were previously computationally prohibitive are now becoming much more feasible.
And it leaves us with some really intriguing questions for future research.
Oh, absolutely.
Things like exploring different configurations of the Mamba module, or optimizing those token reduction strategies for specific tasks.
And perhaps the most profound question is, how will advancements like Storm change the future of AI's ability to interact with video data?
Yeah, how will it reshape our understanding of the world captured in those countless hours of video footage?
It's an exciting time to be working in this field, that's for sure.
It really is.
There's so much potential waiting to be unlocked.
Absolutely. And on that note, I think we'll wrap up this deep dive.
Sounds good.
As always, thanks for joining me.
My pleasure.
And for all of you listening out there, keep pushing the boundaries of what's possible with AI. Until next time.
See you then.